Hello, everyone. A quick show of hands. How many of you are professional Android developers writing apps? Great. And I'm sure you must have heard about Android Oreo's background restrictions. So this talk is about background in general. And I will actually start from basic concepts and cover some use cases and a lot of best practices. My goal is to cover everything in Android background. And I hope that after this talk, you'll have a good understanding if you're having some questions or some doubts about that area. There's also a very fast-moving talk, so I'll move very quickly. If you have any questions, you feel free to get me after the talk. Let's get started. So what does people actually mean when they say running in background in Android? There are different views to it. So there could be running off the main thread on a background thread. So that's one very common use case when people say running in background. Or it could be running for a short time after the user has left the app. So you still want to do some processing when the user is not actively interacting with the app. Or this could also be a case where app is not even visible, not even there, but you are reacting to a FCM, a Firebase cloud message, or a broadcast, or even an alarm. There could also be a requirement to do some kind of periodic sync with the server. So you may want to run it when your app is no more there, but you may want to periodically wake it up, run something, get some data back. Or this could be some other scheduled job of some other kind, not necessarily network, but something else. Or it could even be playing music or doing something like that for which you may need a foreground service, even though technically not background, but essentially in that case, the user is not interacting with your app. So I almost categorize this as a background use case. But let's take a step back and see how the system, that is the platform, views the app in these scenarios. And that's the process state I'm going to talk about for a little bit here. So there is a foreground state of a process where if you're running an activity and it's in the resume state, the platform thinks of your process to be in foreground. This could also be the case when a service is actually on start is called on the service for a very brief time. There could also be a visible state of the process where your app is running, it's visible to the user, but it's not actively doing anything. It could be like pause is called on your activity, or you're running a foreground service. It could also be a service process where nothing is visible, nothing is running, but your service is running in the background, and that's called the service process. And then also a cached process, which is not so commonly seen, but it is the most commonly seen process state by the system. So if you have, in a device, you have dozens of hundreds of apps running, chances are that most of the processes are actually in this cached state. But the first two states are important for this discussion because when I talk about background restrictions, these two states are the states which are known as the foreground state when the system sees the process, whether it can run a service or not. So I'll come back to it in a little bit. And then I already talked about the cache state, where most of the processes running on the device will be in the cache state at any given time. But let's just move into a concept of threads. So of course, in Android, there are various ways of doing threads. And generally speaking, there are four main types of threads in Android. Of course, Android developers will be familiar with the UI thread or the main thread. This is the thread on which your app runs. This is the thread where all the callbacks of the systems are called, from the system is called. And this is where the UI updates take place. This is the only thread that can actually do a UI update on the app. There's also these binder threads, which are also system threads. They are usually seen only in the case when you have a bound service, and that bound service is called by an external process. Some other app calls into that bound service, or you have a content provider where some other process calls into that content provider. All of these calls happen on system-provided binder threads. So binder threads are only useful or applicable when you are having inter-process communication, not usually seen in most of the use cases of the apps. Then there are so-called platform-managed worker threads. And I call them platform-managed even though they are regular threads because there are some constructs provided by the framework that enable you to create those threads. Things like async tasks or things like IntentService, which you use the system API to call to create them, but they are just regular threads. But the number of threads are somehow limited by those API surface. And then there are app control worker threads in which you can create your own thread pool. You can even, like, if you're using async tasks, you can use your own executive service right there. So you can basically create your own worker threads any way you want. At any given time, Your app runs mostly on the worker threads. The UI thread or binder threads are mostly for system callbacks. So as any Android developer would know, you want to quickly go over to your worker thread and do anything you want to do, which is slightly long term on those threads. All right, with that, there are different concurrency and async constructs provided by the framework. Of course, there is well-known async task, which is a convenience way of moving the content from, or moving the processing from main thread to worker thread and back and forth. There are some issues with async task. I'm not going to go into too much detail about them. Most of the issues are the way people use it. It leads into some kind of either memory leaks or some other issues. But that's aside. There is also a looper handler mechanism in Android. This is one of my favorite ways of doing threading in Android. It's also very central to Android. I don't see this being used very often in apps, but if I were to give you like a 30-second update on what this really is, a looper is nothing but a thread with a message queue. That's all there is to it. So there's a message queue, and a looper is just tight loop on that message queue. And a handler is a piece of code which is actually interacting with this looper. So on the handler, you have code to send message to that message queue or process message from that message queue. So that's all there is to it. So with these two, you can pretty easily create a worker thread, creates its own message queue, and then run a loop on that. Android app really is nothing but a looper. It's a looper which is getting messages on its so-called UI thread or main thread. That's all basic. That's central to Android in some ways. You could also use your own executive service if you're using Java. You create your own thread pool there. There are a lot of convenient libraries that provide worker threads for you. You don't have to do anything there. So like Retrofit provides some background threading for networking. If you're using RxJava, of course, there are convenient ways to create worker threads. You can observe something on a worker thread, and then it emits message back to the main thread. There are schedulers that you can use to switch between different thread pools. So there are various ways of doing multi-threading, and there are much more. I'm just covering some of them. But what do these constructs really have to do with the states that I just talked about in a little bit? So there are, of course, process states. I talked about them. And there are also component states. So your activity goes through a state transition, your fragments and your views and so forth. Nothing. You can essentially create as many threads as you want. But the process states and the component state is only governed by what the user is doing with the app and how the system is viewing your app. So between these two things, you can have as many threads, but the app can easily go into the cache state, even if your thread is actively doing anything. So each of these multi-threading approaches have very similar issues to deal with. No matter which approach you take, they run into similar. Some of them provide abstractions to help with those, whereas some like async tasks make it easy to make common mistakes. But there are very similar concerns. So activities, fragments, and views, as you know, are routinely destroyed and recreated. So you rotate the phone, the activity goes away, and a new one is created. So if you're doing multi-threading, you have to be aware of that. You have to make sure that you're not holding on to the stale reference of an activity which just got destroyed. If you're running a background task, you may also want to stop that task when it is not needed. So your main activity goes away or your main processing stops, but you may want to stop the background because you don't want to continue to burn battery for no reason. At the same time, which is more likely, if you started some processing, you may want to preserve that work somehow. You don't want to just completely stop that and throw away the work that was done in the last 5 seconds or so. So you may want to do all of that. So the question is, how do we actually deal with that? But before we do that, what are we really trying to do with this? So as I mentioned, the most important thing that Android developers deal with is to get off the main thread, get off the UI thread, and do something on the worker thread. That's easy. But then you also have to post the result back to the main thread so that you can actually show something to the user on the UI. That's a very repetitive pattern you'll see, and that's the reason why you look into all these multi-threading aspects. So let's take a simple example. I'll walk you through this sample in which it's a really simple sample. You can sort of apply it to any other example that you have, where you have a app in which it is getting the latest value of a stock from the network server, and you want to show it to the user whenever the stock changes. So in this case, you would want to start a background thread because you want to fetch something from the network. You want to periodically get the stock price. You want to update the UI, but only update when the UI is visible. So you don't want to try to update when the activity is no longer there or the fragment is hidden or something like that. You also want to survive rotations or configuration change in general. So you don't want to kind of crash or destroy something or leak something. So you want to do that. You also want to preserve the work. So assume that you downloaded the latest value of the stock and you're running some algorithm to kind of do some calculations on that. You have done that in a background thread, and you want to preserve the work. You don't want to throw it away even when the app goes away, at least for a few seconds. But you would also want to stop cleanly when needed. So you don't want to run forever. You don't want to run unnecessarily. So you want to stop also. So as you can see, even in this simple sample, you have a lot of these requirements that almost everyone has to contend with. And there are various ways of doing it, and this is where people make mistake. So with this, I want to introduce a best practice to do these things using Android architecture components. Yesterday, you may have attended a talk where we talked about architecture components in depth. There was also a ILT, a training that was there on architecture components. Here, I'm going to give you a brief, very high-level overview of that. And if you missed the training yesterday or session yesterday, I would recommend you go back and listen to it again. At a very high level, I'm just talking about two components here for architecture components: view model and LiveData. A view model here I'm using almost as a holder for LiveData objects, and the LiveData is essentially a lifecycle-aware component where it is tied to a widget or a view element on the activity, and it knows when to update that. So it automatically updates because it's aware of the lifecycle of that component. That's at a very, very high level. And as you can see, the scope of the view model is associated with the activity, but not the instance. That's the critical difference here. So even if the activity instance is created and recreated, the view model will survive that. So it survives the entire life cycle until the activity finally goes away. The user clears it up or finishes call or system kills it. But in any other case, the view model preserves the state of the data alongside the lifecycle of the activity. And I said live data is lifecycle aware, so it knows when is a good time to update the UI. So with that high-level background, let's just look at some code here. So yesterday, if you had attended the talk, we talked about different tiers of architecture, a best practice, so to speak. And one of them was a repository, which is basically a set of classes which deal with getting the data either from the network or from the database and making the data sane for you in one place. So this is really a naive sort of implementation of that. I'm calling it Stock Manager. And in this, what I'm doing here is I'm creating a worker thread. I'm using a handler thread class in Java, in Android, sorry, which creates a worker thread for you. And essentially what I'm doing here in the handle message is there is a listener that is attached to it, and I'm calling that listener every time there is a price change. In this case, I'm only incrementing it, but in the case of price plus plus, you can think of going to the network and getting that value because this is running in a background thread. There's also this request update method, which somebody will call, a client will call in, and they attach their listener to it. And there's also this remove updates where the client goes away and they remove their listener. And I'm actually using handler.postDelayed here, which is resulting in sending the message to myself where I'm checking if there are no more clients. If there are no more clients, then I'm actually stopping all the work. So it's a pretty straightforward way of actually cleaning yourself, either giving some time or looking at the state of your clients. The good thing about this class is that it has nothing to do with Android. This is pretty standalone repository kind of class which you can test in isolation. So with this, I'm able to start a background thread, and I'm able to periodically get the stock price update. A view model, as I said, is a class that is associated with the activity. And all I'm doing here with view model is using it as a holder for my live data. The live data is actually just a piece of a data that is holding on to the stock price. The live data class is a little more interesting. So first of all, here I'm creating my listener. Remember the listener that I attached to my stock manager? I'm creating it here. And whenever the callback is called, I'm doing a post value. A post value is live data method which is used from the background thread to update the value of the live data object. And then we have these on active and on inactive callbacks. The on active callback is called when there are active observers to this live data. And I'll show the observers in a little bit. But as soon as there is an active observer, an on active is called. So I'm requesting the updates to my stock manager. And on inactive is called when there are no more active observers. And in this case, I'm removing the listener from it. If you remember in the stock manager class, I'm stopping the work there. If you look at the activity class, there is all I'm doing here is basically getting hold of a view model. And this view model is the one that I said is associated with the activity in general. And then I'm creating an observer. And with this observer, I'm observing the live data which is there. So this is where I begin to get the updates whenever the live data changes. So that's all there is to it, essentially. So you can see there are 3-tier model, a repository, a view model, live data, and my main activity class. All right. So as you can see, with very few lines of code, I'm able to achieve all of this pretty easily. I'll share this slide deck and some code after the talk with you. So a best practice here is to use any background thread mechanism you want, but be aware of the UI update issues and also component and process lifecycle. So that's the key here. But people say, OK, what about IntentService? So there is IntentService which we have been using, which essentially is nothing but a hybrid of a handler thread and the service component, which is a very nice way of actually doing some background work. However, IntentService is just a started service. And started services don't run freely anymore with Android Oreo. With Oreo, the service will stop very soon after your app is not in the foreground. And you cannot start a service if you are not in foreground. So app can be in temporary whitelist state. There are some states defined, whether you're handling a high-priority GCM message or handling some kind of an SMS. In those cases, you are in a temporary whitelist and create a service. But that's very, very rare. In most of the cases, you will not be able to start a background service from background. So what is foreground again? So if you remember, I showed you the states here. Here is a more comprehensive view of it. I'll not run through every line here, but at a very high level, you can see that there are only 2 states where the app is considered to be in foreground. So there is an activity running in a started or a resumed state, or a service which is running with a start foreground. Other than these 2, your app is mostly in the background state. So in other words, unless the user is actually seeing something, you are in background. And in background, you cannot run a started service, including the intent service. So if you're wondering how do I know what my state is in, you can always run dumpsys command shown here. In this example, I was running a background service with a foreground activity. When I ran it for the first time, the first line, my state was foreground, and the process state was stop-activity. And the second one was when the activity went into the background, and the service was still running. And the last one when the service actually stopped. So, but what are we really trying to do with background services in general? So a good example for that is that I was running my app, and I was running something in the background. And the app goes to the background, but I still want to finish what I was doing. I want to continue what I was doing. I don't want to just stop it right there for a little bit more time. So with that, I want to introduce a best practice for using a job intent service. If you're not familiar with job intent service, this is a new construct added in support library 26.1. The way it works is that if you use job intent service, in the pre-O devices, it runs as a normal intent service. So it behaves exactly the same if you're familiar with intent service. If it is running on O or later devices, a job is dispatched via a JobScheduler.enqueue method. And it will start almost immediately because it uses a new method which is called setOverrideDeadline with a 0 there. So it will immediately start processing almost as if it is a job, as if it is an intent service. So here is a simple refactor. If you're familiar with intent service, you can easily convert it into a job intent service by just extending the job intent service. Instead of calling start service, use enqueueWork. Instead of having onHandle intent as your callback, use onHandle work as your callback. And in both the cases, you will be called on a worker thread. So the worker thread is automatically created for you. So it basically does the same thing as intent service, except it is more robust and backward compatible as well. So for any background work that you want to ensure finishes after your app is no longer visible, use job intent service. So, but if you really want to use a background service for something different, like for example, syncing of data. So your app is no longer there, it's no longer visible, but you still want to sync data periodically, or you want to sync data after some time. So that's a valid use case. But be aware of those and app standby. So this was a new feature, or a feature that was added in Marshmallow, and it's been progressively increasing in complexity. Where if the screen is off or stationary and not plugged in, you will not get any network access, and the wake locks are ignored and so forth. So I'm sure you're aware of it. I'll not go into too much detail here. But be aware of that. So even though you want to run something in the background, chances are that you may not be able to do what you want because of these restrictions. Here I want to introduce JobScheduler. So I'm sure people, you're already familiar with JobScheduler, but real quick, it is for any background work that you were using a started service before, I would strongly recommend to use a JobScheduler now. Why? Because it works well with the DOS maintenance windows. You will get complete network access and everything else you wanted to do in a very nice and efficient way using JobScheduler. You can also specify conditions when you want your service to run. So you can say what network type needs to be there or what should be the retry policy. In fact, with O, we added some new constraints in which you can actually say that run only when there is a certain battery available, run only when there is enough storage available on the device. So you can have additional constraints to run your job. That's really, really valuable. So for most longer running background work, for which you were using a started service before, use JobScheduler. Foreground service can also be used for a user noticeable, longer running task which does not need user interaction. So an example of this could be a media app. So you want to play some music or something like that, or a navigation app where you want it to be running, basically even when the screen is off, use a foreground service. You may also promote a background service to a foreground service by calling start foreground service, or a new method defined in context. New method defined context, creates a foreground service while you are in background. So you can do that in Oreo and above. But the most important takeaway from this is that do not surprise the user. So you should not be using foreground service when the user is not expecting it, because foreground service will need to post a notification to the user. So when they see that, they should be able to relate to it. That yes, of course, I use this. I need this. So let it run. I'll just quickly skip over a few things here. Sync adapters is another Android construct which you may already be aware of. But I'm talking about it very high level because this is sort of a legacy mechanism. It is somewhat cumbersome to set up. And it's only useful if you're already using content providers. And the content providers essentially is again another Android component which should really only be using when you want to expose your content to another app on the device. If you don't have a use case to actually exposing your content to other applications, you really should not be using content providers. So instead of that, you should use a combination of JavaScheduler, Room, or some similar library for your database, and your own sync logic. So that is what I would recommend if you're not already using sync adapters. Another important construct for background is alarms. Use them sparingly, as I said. It is a system-level service which you can use to send a pending intent to your app, and it can be triggered with inexact or exact times. But remember that your app may actually be in background or when handling a pending intent. So if you were starting a service before, you will not be able to do that anymore. You can, though, send a broadcast to your receiver. And while you do that, you can post a notification to the user. So if the user interacts with your notification, at that time, you can definitely start a service. Or you can do something else, like with the notification, you can take the user to some activity. Like they were expecting something and they see the activity. Or you can even start a foreground service if that makes sense for your use case. You can even schedule a job with JobScheduler with an alarm. And you may even use a set alarm clock functionality for a user visible clock event. But like I said, for all of these cases, you have to be very careful to use Alarm Manager for only when you really want to be doing something at a specific time. But for all other cases, I would say use JobScheduler again. This is a very useful construct which system manages really, really efficiently, and you will be able to do most of the things that you were doing with either service or alarms using JobScheduler. So really high level, I'll not again go into too much detail of this chart, but this tells you what is actually happening when your device is in app standby or light dose or dose mode. Most important takeaway from this, as you can see here, is that there is no network. In any of these states, you do not get any network. Even though your alarms may fire, even though your app is called back, but you don't have any network. So there is really no useful use when you actually are in, let's say, dose light mode and your alarm fire. So try to stay away from those scenarios and make use of JobScheduler again. I'll wrap this talk up by talking about Firebase cloud messaging. So at very high level, there are two types of Firebase cloud messaging messages, a notification message and a data message. And both of them can be sent with normal and high priority. A normal priority FCM messages are batched for those maintenance, whereas a high priority FCM message can interrupt those and apps standby. However, you should only use a high priority FCM message when it is absolutely critical to notify the user about something. For example, a new email has arrived or a new text message has arrived. Let's talk about some best practices here real quick. Do not use high priority FCM unless it is a user critical. I already said that once. You should use normal priority FCM messages for any notification message, for any minor user update. For any data updates, and this is very important, for any data update, even if it is like a sync message to your device or to your app, try to use the payload of the FCM message itself. This is very battery efficient, and you will be able to do a lot with 4K. So try to send all the payload to your app, and then the app can update itself over time. If it is absolutely necessary to fetch any additional data after an FCM message, then either use a job intent service or schedule a job to get that data. But again, always notify your user when you're using a high priority message. So today, it is possible to not do that. But as you know, that Android is moving more and more towards scenarios where we don't want to surprise the user. We want to preserve the battery. So expect that there will be some more restrictions on these lines. So be prepared to handle FCM message in a way where you're actively notifying the user as soon as you have a high priority message. So with that, it was a very quick talk. I actually covered a lot of ground on various background scenarios. But with all of these best practices, I would urge you to go back and look at your app again and try to see if you can fit in any of these best practices. If you still have any questions or concerns, or if your use case doesn't fit into these things that I mentioned today, feel free to talk to me after this session. I'll be here, and I'll also be at the office hours. Thank you.